Hello, hello everybody. In the last video, we discussed about what LSTMs are, and we have a very deep dive session on it. We covered everything from why do we felt the need of having something like LSTMs, why RNN didn't work out, why what are the different notations in LSTM architecture, and what the hell is LSTM architecture, because if you just look at it, it's really scary. But if you see RNN as compared to LSTMs, then RNN is very simple. Now, in this video, we will cover something called GRUs. Its full form is Gated Recurrent Unit. Now, I would highly recommend that if you haven't watched the previous video, then just go and have a look at it, because most of the things that we discussed in LSTMs will also follow here, though I will break down everything in this part as well. But uh, just to be more clear, this will help you. If you have covered this part, then this part will be way more easier for you. But it's okay if even if you don't want to have a look at it, we will cover everything here in detail. And as I promised in LSTM video, and I think it really helped you this time also, I'm promising you that this video, if you will watch end to end, start to end, then all your doubts around GRU and howsoever complex its architecture may look, but by the end of this video, everything will become simpler. So let me just paste the GRU's architecture from internet. This one looks good. Yeah, I think we can pick this up. Let me copy this image, go back to my whiteboard and paste it here. And let me crop it a bit because there's some additional information that is given here which is not required. This is done. So this is the architecture of GRU. Now if you have looked at LSTM's architecture, then this looks very similar to it, but there are differences. And I know there are some additional terms here like RTZT, H tilt T. This is called tilt, and we see additional pointwise operator here. Everything will be discussed. So let's first understand that why do we felt the need of having GRUs and why LSTMs were not helpful. LSTMs are helpful, but the problem is that LSTMs have a lot of weights. There are three gates, and within those three gates, there are single layered neural network with nodes which are decided by you. But if you pick a large number of nodes, then since you have three gates, so that becomes three times plus the biases. So overall, there are a lot more parameters. And when you have a lot of parameters, your training time increases. But in GRUs, what is happening that instead of three gates, you have only two gates. So since you have only two gates, your training time will reduce because you will have lesser parameters, right? So this is one of the benefits of GRUs. Now, if we compare performance of these two, so we can't say that LSTM is better or GRU is better. That depends on the data that you have. So they behaves in a way that you would have to experiment. There is no certain rule that GRUs are better than LSTMs or LSTMs are better than GRUs. You need to apply GRUs and LSTMs on your data and then decide which one is giving better results. But This one, GRUs, this takes lesser training time as compared to LSTMs, and the performance is comparable. It's not like there is a lot of difference. Differences may come depending on the data that you have, but in general, the performance is comparable. So let's go in depth of this GRU architecture. And there are not only one difference of having only two gates, there is one more difference, as you might have noticed up till now, that here we just have a single state HT. We have no cell state. There is no separate cell state for storing the long term memory. We only have a single state which is maintaining both short term context and long term context. Okay, so these are the two main differences in GRU, right? Now let's dive deep into it. First, as we will follow the same pattern as we used in LSTM video. First, I will introduce you to all the notations that are there in this architecture. So there are two inputs. First one is xt and the second one is ht minus 1. This xt is the input at time step t. Okay, and I think I don't need to tell you this, but if someone who hasn't watched the LSTM video, this will be a vector. For example, let's say you have a sentence that I love apples, and let's say you are at time step 3. Then this apple will go as input, but not as a word, but as a vector embedded. So it's just a numerical representation of this word carrying its semantic meaning as well. So it will look something like 0.413, etc. Whatever you have decided as your dimension. So if you have decided it as 3, then this is how it will look. So this is going as input, and second input is your ht minus 1. This is your previous hidden state. Hidden state at time step t minus 1. What will be your output? Output will simply be ht. That is your hidden state at time step t, or the current time step. Okay. And now comes what's happening in the processing part. What are the notations that are being used there? So these boxes are nothing but single layer of neural nodes. Okay. These are the single layers. So let's say you decide that your neural network will have 3 nodes, then this is how this box will look. And this sigmoid and tan h represents that activation function in each of these neural nodes will be sigma. If it's tan h, then every node will have activation function tan h. And as I told you in the LSTM video, this sigmoid function decides that how much percentage of the information should pass, right? So let's say you have this as your information. Let's say this is 1 cross 3 vector, and let's say your sigmoid function gave values like 0 0.2, 0 0.4, 0 0.1. So what does this mean? This means that 20% of the information will pass, 40% of the information will pass, and 0.1% of the information will pass with whatsoever you are multiplying it with. So if you are multiplying this with this vector, that would mean that from the first element, 20% of the information will pass. So this sigmoid decides that how much information should actually flow. And this tan h is the actual information that is flowing. Actual information that is flowing. Okay, so this is the difference between these two activation functions, and the difference will become more clear once we are done with notation and we are actually understanding how the architecture is doing the processing. Next, we have these pointwise operators. So I think this and this part is already clear. This is pointwise multiplication. So if you have two vectors, then you just multiply the corresponding elements, and the new vector that you get, that will be the product of pointwise multiplication. Similarly, instead of multiplying, if you add these corresponding elements, then that will be the result of pointwise addition. Now here we have one additional pointwise operator which was not there in LSTM, and that is 1 minus. This is pointwise 1 minus. And what this is doing, let's say you have a vector 0 0.4, 0 0.2, 0 0.1. Then if you apply this 1 minus pointwise operator on this vector, then your value will be 1 minus 0 0.4, 1 minus 0 0.2, 1 minus 0 0.1. And I think only one part is left, that is, what is this RT, ZT, and HT? So these are nothing but the output of your neural nodes. So if you have this neural node, then you will get certain output from here, certain output from here, certain output from here. This will be single element. Let's say you got a value of 0 0.4 from here, or 0 0.2 from here, or 0 0.1 from here. And if I just keep this in a vector form, then this becomes your RT, your ZT, and this HT tilt is output of this neural network where you have tan H as activation function. Okay, and as far as their names are concerned, this RT is called the reset. This is actually, this part is actually acting like a reset gate. Okay, so that is why it starts with R. You can call it reset state, but this is not actually the naming convention. You can call it whatever you want, but this R is actually coming from the reset part, because this gate is doing the reset thing. We will understand the architecture. This ZT represents what comes before that goes as input in the update gate. So here we have only two gates. The first one is the reset gate. Here we have the reset gate, and here we have the update gate. In LSTM, we had three gates for get gate, input gate, output gate. Here we have only two gates, reset gate and update gate. And this HT tilt looks very similar to C tilt T, right? You remember from the LSTM video? So this is nothing but candidate state, candidate hidden state, candidate state, whatever you like it. Okay, so I think the notations are clear, and I think we can dive deep into the architecture now. Let me clear the mess that I've created here, and let me, can I just copy this part? Uh, okay, let me just clear this part. I don't know why, but this is not working. I will skip this part, otherwise your time will waste, or you can just bear with me. Okay, so in order to understand this architecture, what we will do, so what is happening here? I know this looks a bit complex, so let me just pause my video and let me redraw it. Just give me a moment. Okay, so this is done. Now let's understand the architecture here. To understand this, what we will do, that we will follow the same approach that we used in the LSTM video. First, we will see the reset gate part. Then we will see what's happening in the update gate part. And finally, we will see how the output is coming. And what's the output here? Hidden state that contains both the short-term context plus the long-term context. So we will see how the reset gate part is happening, then how the update gate part is happening, and how we are finally getting the output, right? So the first step that happens here is that we find what RT is. So we take here, so this is our RT. I'm highlighting it here. This is the RT. And how we are getting it? We are getting it through two inputs. The first one is this HT minus 1, that is the previous hidden state. And this is XT, that is the input at current timestamp. This goes as input in our single layered neural network where we have sigmoid as activation function, and what we get as output is actually a vector called RT. Now, we I think we left the assumption part here, and that is how these dimensions and these neural nodes are decided. So every vector that you see in this architecture except the xt1, every other vector, whether it's xt minus 1, whether it's ht, whether it's h tilde t, whether it's zt, whether it's rt, every vector that you see here except xt will have the same dimension. This is the rule of GRU, just like we had this rule in LSTM. Every vector will have same dimension. Okay. And this dimension will be equal to the number of nodes that are there in the neural network. So let's say you decide that your neural network will have 3 nodes, then every vector here will be of dimension 3. These number of nodes are decided by you. Okay. And this xt depends on your how you have performed your vector, how you have obtained your vector embeddings. So this can be of any dimension, right? And I think this was the main assumption. In case I missed anything else, I will cover in the video as we move forward. So what we are doing, that let's say your ht minus 1 is of dimension 3 and your xt is of dimension 4. So this constitutes your xt and this constitutes your ht minus 1. Now since your ht minus 1 has 3 elements in it, that means that we decided 3 nodes for our single layer neural network. And this will be a fully connected artificial neural network, right? I'm not drawing all the lines, it's fully connected. And the output that you are getting, we are storing it inside a vector called RT. And so I think the first mathematical step is clear, and the intuition behind it is that this vector will decide that how much information will actually pass. From what we will see next. Now we are getting RT from here, and from here one input is coming, and that is HT minus 1. So this was our step 1 where we will calculating RT. The second step is that we are doing pointwise multiplication of HT minus 1 and RT. What is happening here? That we are deciding that how much information from our previous hidden state should actually pass. And who is deciding that how much information should pass? This RT. And this is what completes our reset gate part. Reset gate part. So what actually happened here? That you had your memory from the previous time step where you had long-term memory plus short-term memory in your hidden state. Now based on your current input, xt, you want to incorporate that short-term dependency here. You are incorporating that short-term dependency here. So let's say there was a long story and suddenly some new input came. Maybe like a king's son was born. So this is a new twist in the story, right? So whatever history you maintained, now you are incorporating that short term dependency into it, and you are dropping the irrelevant information that is no longer relevant to you from the history that you maintained. So it's like resetting. You are dropping the unnecessary information, irrelevant information, and allowing to pass only the information that is relevant based on the current input that you have got. Okay, so I think the reset gate part is clear. I'm again repeating this thing, that with reset gate you drop the irrelevant part of the history that is no longer relevant now. You're dropping that part based on the input that you have got. Now let's move ahead in our architecture. So this is our updated state. Okay, this is our updated state. So this is ht minus 1 plus rt. This is our updated state. And what do we call it? We call it, it has a special name, and we call it modulated hidden state, modulated hidden state, or reset hidden state, or reset hidden state. Okay, now this hidden state, along with, not alone, but along with xt, this xt and this reset hidden state goes as input here. So what I'm saying, that, let me again pick this architecture and paste it below. Just hold on with me for some time. You can skip this part. I will not waste my time in editing, because creating this video takes a lot of effort. I do a lot of research for creating videos like this. So if you are liking this video, please give it a thumbs up and subscribe to my channel, because that gives me motivation. I know I hardly get views on the videos that I create, but I still do it. So we understood the reset part, and now we are reaching to this stage. What we are doing here, that we are taking our reset hidden state, and we are taking our xt as input, and we are passing it through a neural, a single layered neural network, where every node has activation function of tan h, and the output that we are getting from here is a vector which we call ht tilt. Okay, so what's exactly happening here? I think the mathematical part is clear. This tan h is giving output, that what's the actual information that flowed? What's the actual info? Actual info, not what percentage should pass, but it is the actual information that is flowing. That is flowing. So what exactly is it telling us? So we dropped the irrelevant part, and now we have our updated memory, right? Now, based on this updated memory and the current input that we have got, what do you think? We are asking this network, what do you think, that what can be the possible inputs that we need to add in our hidden state? So this is like the candidate state. Just like when elections happen, then there are various candidates who stood up for a particular, uh, who who contest elections for a specific post, but out of all the candidates, only few are selected for that particular post. Or let's say there are elections that are being held for various ministries, then out of all the candidates, only few people are selected who actually become the ministers. So here you are just getting the information that this network thinks that should be added. Okay, it gives you all the possible information that should be added. And of course, we will not be adding all the information into our hidden state. We will be adding only the information that is relevant. But this tells you that what information can be added. Okay, so this is giving us the candidate state, right? Now we have got this candidate state. What we are doing that just like we find out what RT is, same way we are taking XT and we are taking HT minus 1 and we are calculating ZT through our sigmoid neural network layer. Okay. Now from this ZT, if we do pointwise multiplication, if we take this ZT and we do pointwise multiplication with HT tilde, what we will get? So this is the information that we think that it should be added to our hidden state. But what this Z is doing, from where is it coming? From the sigmoid activation function, right? So this will decide that what information from this candidate hidden state should actually be added in our hidden state. Okay, so this is the information that we will actually put in our hidden state. But now here's the catch. We are doing one additional thing here. We are not just simply putting the information in our hidden state. We are doing one additional step here. And that is, so this was the part of update gate. But this is just the half story. One part is also left in update gate, and that is this part. We haven't discussed this part up till now. Yes. So what we are doing here, we are taking ZT and we are doing pointwise operation on it, 1 minus pointwise operation on it, and then we are multiplying that information pointwise operation with this, and then we are adding the information. So I know a lot of confusion might have happened. So let me put it mathematically here. What we are doing, that we are taking ht minus 1, this is how it's coming, and then a pointwise multiplication is happening. With what quantity this happening? With which vector is this happening? This is happening with zt, but there is a pointwise 1 minus operation that is happening here. So what we are doing, that we are doing this 1 minus zt. This 1 is actually a vector of 1. So if there in zt there are 3 elements, then this 1 will be actually a vector of ones with 3 elements, 3 ones. Okay, we are doing this, and then what we are doing, that we are moving to our next operation, and that is addition, and we are putting up the information that we have got. This is what we are doing mathematically. So I think this part is clear. Out of the candidate state, we are deciding what information we should actually put in our hidden state, which we think is important based on the inputs that we have. So this part is clear, but the problem is this part. What we are doing? Why we are not just simply adding this information is ht minus 1? Why this special operation? Let me highlight this with a different color. Why this special operation? Okay, why we are doing this special operation, and why not simply doing this ht minus 1? I am sorry, let me pick another color. Why not simply this ht minus 1 plus this part? Why we are not simply putting the information in a hidden state? Why we are doing this additional step? So the reason is very simple. Do you remember what was the problem in RNN? We had only single state, HT. Because of that, and RNN suffers from a very serious problem, and that is the vanishing gradient problem. Vanishing gradient problem. And that was the reason why we moved to LSTMs, where we were maintaining two states, hidden state for short-term context and cell state for long-term context. But In RNN, we had only single state HT, and RNN suffers from a very serious problem called vanishing gradient problem, because of which is it was not able to retain the long term memory, right? Because the gradients used to decay so fast that after a certain number of steps, it was not able to remember what happened previously. The gradient used to become that much small, used to become close to zero, that it was not able to learn the weights that were much older, or that were coming way back in the time, right? So because of this vanishing gradient problem, RNNs were not able to maintain the context, especially the long term context. But here in GRUs, we are saying that we are just maintaining a single state, and still we are saying that its performance is comparable to LSTMs. How is this possible? We are doing exactly what we were doing in RNN, but still we are saying this. So the reason is that because of this step that I'm highlighting here, 1 minus SETI, the 1 minus pointwise operator that we are applying on our previous hidden state, because of this operation, it is preventing the vanishing gradient descent problem. This solves our problem of vanishing gradient descent. So let me copy this statement and write it here. HT minus 1, the previous hidden state, that is having a crosswise multiplication with 1 minus ZT, and then we are adding it to HT, that is the candidate state, with ZT, and we are saying that this solves the problem of vanishing gradient descent. Before discussing that, there is one more benefit of having this quantity, and that is this complete operation incorporates both the forget gate and the input gate of LSTM in just one single operation, which we are calling as update gate. So this part is actually telling us what information do we need to put in our hidden state, previous hidden state. So this is acting like input gate of LSTM, right? And this part where we are deciding that what information from previous hidden state should actually flow, we are applying a filter. This is acting like forget gate. So a single gate, the update gate of GRU, is solving the purpose of input gate and forget gate both. That is why this is beneficial here. This part is beneficial for us because this is efficient. We are having lesser parameters, but this is acting very similar to how LSTM acts, right? So with lesser parameters, we are doing the work of two gates in a single gate. So this is one benefit, that is efficiency. And the second benefit, which is the most beneficial one, and that is prevents vanishing gradient problem. We're facing in RNN. We are not facing this problem here because we have this additional quantity 1 minus ZT that prevents gradients during backpropagation from decaying, and those gradients remain same. Instead of vanishing, instead of reducing in their number or quantity or size, whatever you may call it, instead of reducing in their value, they remain same because of this quantity. Because this ZT becomes close to 0 whenever, then this becomes close to 1, and because of which the gradient does not change. The gradient does not change. And if there are many gradients, then those gradients will not change. So I think this part is clear. Because of this quantity, we are getting a kind of balancing mechanism that is helping us to remove the information that is there in this part ht minus 1, and this part is helping us in adding up the information. So basically this is acting like a balancing mechanism. Whatever we are adding, that much space must be present in our hidden state. So we need to remove that much part that we are adding up. It's kind of a balance that we are creating. And what's the result of it? The result is that the vanishing gradient problem that we were facing in RNN, that no longer exists here. So I think this entire architecture, the entire explanation that I gave you around GRUs is clear. If you still have any doubts, do let me know in the comment section and I will try to help in the best possible manner. This video took a lot of hard work. So if you like this video, please give it a thumbs up and please subscribe to my channel. Thank you.